Hello.
Hello. There's nobody.
Hello. Can you hear me?
Yeah.
All right.
Can you hear me? Yeah.
Yeah. How's going?
Good, good. I still haven't done this assignment yet. Need to.
I'm trying to do.
Yeah. I need to think. I want to think of something to do. I haven't even really thought about it.
I just trying to do something super simple, but it's not working.
Yeah.
Frustrating.
I'm just gonna try and do the mosquito on the Raspberry Pi this afternoon.
Yeah.
Yeah, I think so.
I like now. I'm just trying the ISP thing.
The what?
Then the ISP, like a SPI communication,
Oh yeah.
with just with two Arduino, and then I wanna make a soft access point with ESP8266, which I haven't done yet.
You mean like some way you can connect to it, where it is the Wi-Fi network?
Yeah, it's kind of like emitting. It's like you're connecting to it, and then you're connecting to the router. It's like a
Yeah, yeah.
virtual.
There's some libraries called like Wi-Fi Manager and stuff. You can just download it and install it. It's super easy.
Yeah.
Except if you want to code it from scratch, go for it.
I'm not sure if I'm gonna do that.
Good
Hola,
morning.
Oscarito.
Good morning.
Hello. How are you?
Good.
Not many people yet.
Yeah, busy class today.
A lot of lazy people.
Good morning, everyone.
Hola.
Morning.
Oscar, we put the wrong name to this class. The Osi Model is the most boring name ever. No one will connect.
Yeah, well, I was thinking
Exactly.
that.
I promise you, it won't be about the Osi Model, because we much fun. In fact, it's a class to tell you that the Osi Model, in fact, doesn't exist. It never has been fully implemented. It's a representation, like God, let's say, and we all try to approach it, but we never reach it, actually.
So class is finished then. You told us now.
Well, we'll talk about stacks in general, yeah, but not actually. Okay. I think I guess we should wait.
Let's wait.
Yeah. Anyway, then the class is recorded, so I'm really happy. And of course, it's nice if you are here because we could make it more interactive. Because the class, I mean, at least for people a little bit advanced, I think it's a class that could be quite interactive. If not, it could be used interactively then with video, because we'll run a lot of different commands on our computers to actually see. Okay, so let me just.
Do you guys know if anyone else is going to come, either from MDev side or FA Academy?
I think so, yeah.
I don't know.
Okay.
I'm happy to wait a bit. I mean, I don't think also a class will be that long. So.
Good morning.
Morning, Santi.
I've just clicked on the panic button on the Fab Academy homepage for the first time.
Oh, you have to thank Hala here. She was the one that sent me another website that did something similar, and I couldn't resist but to implement it in the FA Academy.
Yeah, I don't see how it helps panicking, but I like it. Distracting.
Well, sometimes you just need that.
Yeah.
Hey, good morning.
Good morning.
How are you?
Good. And you?
Yeah, good. I wasn't sure about the class, so it's a good news. It's happening.
By the way, Guillem, I changed the name of the class to the Osi Model doesn't exist. Hope you like it. You're muted, Guillem.
Sorry. No, I mean, in a way, it's not it doesn't exist, but at least like it's an idea. So we don't use it fully, but we use parts of it, and it's a really good way of organizing what the network stack is. Okay, so this works super nice. This works perfect. Oscar, let me know when you want me to start. I'm happy to wait. Just so, let's say, I'll wait for you to tell me. In fact, I'll go for a glass of water.
Okay. Well, it all depends on you guys in the class. If you seeing that more people is gonna come, or if you want to start already, like in 2-3 minutes.
Also, the class will be recorded, so everyone could access there. And I will show you. So I tried to make the class by following, of course, my presentation, and everything will be shared after. Okay, I didn't have the time to actually prepare the notes in advance, but it will be shared after. And especially there's a bunch of links if you want to read more, just something specific for a project, because of course the topic we are touching is quite broad, and it's much linked to, let's say, a lot of disciplines in engineering, and I guess you might just want to pick some stuff for your project. So after on the links you will find more information. So yeah, if you want, as you want, we could wait like 2, 3, 5 minutes more. If you
let's wait for 5 minutes. We start at 10:20. Okay.
Perfect. Okay, super. So I'll go for water. I'll be back in a moment.
Yeah, I just sent a message to the students, so maybe they will come.
Sure.
Just for everyone to know, this is going to be basically a class where we try to answer a question, which is simply what happens when you type google.com in your browser and press enter. Okay, okay. So we'll try to map not actually what's going on the Google servers, but what happens from you typing this on your phone, going through a 4G link, then going to the backhaul of your company, then going through another tire internet, going through a submarine cable, arriving to Google data center, back and forth, and we'll understand like all the protocols that happen in here. So you know, for example, what happens when you use a VPN, or what happens actually when you have something that's running on 4G and suddenly you run it on Wi-Fi, and why at the end all the things are the same, or why you could reach the internet by connecting your phone through USB on your computer if USB doesn't look like an internet protocol at all. Okay, so we'll discuss about these kind of topics. So should we start? Yeah, we go. Okay. So I share my screen. Yes, sharing module 1. Exactly, this is, yeah. Okay. So you see, I'm an old boy still using Keynote. I should switch to something more fancy and less platform dependent. So let's go. Yes. Okay. Let me just minimize this. I hate because I don't see the pointer. Sorry. Okay. So welcome everyone. Are we recording, Oscar? I guess it is, yeah. Okay, so I call the class today "What We Learn from Onions" because you'll see we'll talk a lot about network stacks and we'll talk a little bit about how the internet works. And so the way, in fact, all the things are built and what makes it really cool is that you'll see it's basically the idea of putting layers upon layers. So actually, in a way, talking about onions, or at least onions, something that looks similar to it. So I think the purpose for me of that class well, so this is not from the 90s, but I think for many of us, the way we connect to the internet, it's a bit like that, right? I mean, it's like we know we plug into a network before with a wire, through a wire, now with our phones, using 4G, maybe next year 5G, or using the Wi-Fi in or UNIS. But actually, we know feel about what happens on networks. No, maybe now it's not the image of the iMac getting connected. It's this one here where you see like the 3 or the 2 icons in your phone screen. But it looks like networks. It's something we use all the time. But sometimes it's like they're a little confusing. And they're confusing because what I want today is that when you see, again, this kind of images like 5G will change everything. Well, of course it would change things. Of course we need to be aware about it. But we need to also to keep in mind that most or all the networks nowadays, all the systems that we use for communication, they rely on IP technology. They rely on the internet standards, and those are really old. And that's the beauty of them, in fact. Because it means that the web releases open standards, they are fully embraced, and it means that it makes things much more compatible rather than if each manufacturer or each industry will be creating its own standard. So I wonder when you see this kind of things like 5G will change everything, or even something cooler, like for example, IPFS, which is a protocol for building kind of a more distributed web, which I love. You don't think these are things that are, let's say, one separate from the others. They are just layers on the system. Okay, so for me, that's the goal of today's class in a way. It's by answering what happens when you type google.com in your browser and press enter to understand actually what's inside and your computer, what's going on inside the network that connects your computer or your phone with the Google servers, with the Google data centers. And so actually, we in a way demystify the magic, and you are in a way understanding better how all these systems work and avoiding confusions, and especially avoiding buzzwords, because companies like to sell us things telling you it's the next big thing, where maybe it is a new thing and maybe it's big, but it's just part of something bigger. And I think that's important for you when you choose the technologies you want to use. And at the same time, as I always said, like learning a little bit more about the internals helps you to be creative. And that's important, because it's so that you can just apply this knowledge you learned today into the purpose of building networks, of building systems. You could for sure apply those ideas into many other topics and fields on technology and even outside the scope of technology itself. So as I said, we'll talk about onions. I will talk about onions because I want you in a way to explain you a little bit what happens and how the internet protocols are built. And so what happens, let's say, when we type Google, as we said. So this class was called the Osi Model. And as I said before, I decided in a way that this class should also help us to demystify this thing called the Osi model. So, well, the Osi model, for the ones of you that never heard about it, we'll think much more. We'll solve that question about what it is in a moment. But it's basically a way of structuring in layers the way that our computers communicate ones with the others. And by computers, I don't mean just your laptop, I mean your phone, how your phone communicates with a Google server and goes through transatlantic cables, etc., etc. So in order to do that, it's not that we came out with a single protocol, let's say USB. Imagine the internet running in USB. USB hubs in your street, you know, and then another USB hub in your, let's say, the end of your city with all your houses plugged in, and then a USB hub under the ocean. No, it won't work that well. So we built a system where actually what's called the physical layer or the network layer could be changed, right? We could go from 4G to Wi-Fi to Ethernet to fiber optics, and the rest of the protocols could be there. Or even something like where the protocols would be always there, like TCP, and we'll see what it is in a moment. And actually, we could change the applications on top. We could do email, and then we could do the HTTP. And a clear example here is that the email protocol, the POP3 protocol and the SMTP protocol, the one for sending and receiving emails that Gmail and all the other email service use implement, that your clients, Thunderbird, Mail, Outlook implement, it's in fact prior to the HTTP, so it's prior to the web. And then suddenly someone invented the web, but we then had to change everything because they both work on top of something called TCP IP. And so this beauty of layers, right, where you could replace a bit of it and still keep the others, is what we'll discuss today. I say the Osi model, it was never fully implemented because actually in your right, you see the Osi model described with this application, presentation, station, transport, network, and data link. Well, the truth is that at some point, they try actually that the internet will comply with all this. But actually the way the internet and most networks work, it uses a little bit of fewer layers. So we could say that the Osi model, it's kind of a theoretical representation or a way of organizing our networks, but they don't always fully match perfectly all those of these 7 layers. And so maybe it's easier, at least for me, to think at least about the ones that you see on the other side, the standard internet protocol, what's called TCP/IP model, where we have the network interface, then we'll have the network, then we'll have the transport, and then we'll have the application. Well, for sure, the things now might sound new, is still a little bit weird. And so the idea is that we'll go step by step on them. And so we'll learn actually how to implement them properly and how to use it. And at the end, to answer ourselves these questions, what happens when we type Google? I don't want to talk too much about these Osi model and TCP models. So what I want is just you understand that we'll talk about layers, and that as a convention, these layers, the industry put the numbers, or the scientists who actually research on them. So layer 1, 2, 3, 4, 5, 6, 7. We'll mostly talk always about layer 1, layer 3, layer 4, and layer 7, because this is the simplification model, the TCP/IP model. For the ones that are interested in how this came to be, it's a classical example where you have something being developed, TCP/IP, which is developed for a specific purpose to happen right now, and then you have someone else in a more, let's say, theoretical background trying to build a much complex explanation of what it is. And of course, sometimes you need to move fast, and you move fast, you implement whatever you want, and then someone else might actually come out with a much more strict or complete representation of what you are trying to discover, that of course has a much more generic a way of explaining things, or more than generic, it's more general, right? Can cover more use cases. But so let's say I don't want to spend too much time on explaining you why the Osi and why TCP. Just that these are things we use today to discuss about network. I don't know if this is like too hard, let's say too hardcore just to start, but the important thing about the onion and why I use an onion to represent these is that these layers, they encapsulate ones inside the others. So let's go back to our nice onion. So if this onion here, okay, would be, let's say, you right now typing Google. Your request that actually would be, for example, let's say you want to search for restaurants, they're closed. Let's say when the restaurants are going to open in Barcelona, this sentence will be right in the center of the onion. Then around these, you'll have what's the protocol that you use to request to Google. That, as you might remember, it's called HTTP. It appears above your browser bar. And then around these, you'll have what's called usually a TLS, which is the one that adds the S, HTTPS, that's safety. So no one actually could see what actually you are searching in Google. So that's security, sorry, more than safety. So actually it's the one that prevents someone from spoofing this interaction between you and the Google server. Then around this layer, we'll have another one that would be the one actually that's the internet curve. It's called the TCP one. It's the one that tells how your computer needs to talk to another computer. And then it will be the IP one. That's the one actually used not just by your computer and the computer at the end. That's going to be the Google server or servers, also by all the computers in the middle, all these routers, like the one you have at home, but all these other routers in all these internet service providers that will drive this. But then there's still going to be another layer on top of it. That's going to be a layer that it's going to be the one that actually defines the media we are sending the information through. And this media could be, for example, if you are on the street, could be a 4G connection, but when it arrives at the backhaul of your ISP, it might go to fiber optics, and these fiber optics might even change their standards. When it arrive to the Google data centers, it might go switch from fiber optics to Ethernet, which is these cables you all know, and from the cables you will reach the server. And all these changes of different cables and media, so the medium, let's say, changing from copper to fiber, from fiber to the air, all these changes won't affect the core of it, which is just this search we are requesting on Google, which is actually if the restaurants in Barcelona are open. And so today we'll explore this idea. By the way, I don't see the chat when someone types. So if someone is typing something that I need to be aware, Oscar, Santi, or anyone else, please let me know. Okay. So, Oscar?
Yeah, no, I said okay.
Okay, thank you very much. So, just one last bit before we actually jump into, let's say, more the game of actually understanding and playing with those things. It's important for you to understand that everything we're talking about it now is really old. I mean, this dates back from 1968, where the first ARPANET projects started. And so most of the standards we'll discuss today, they are from the 80s, in fact. TCP, IP, the HTTP, it's from the late 80s. Of course, many, some of them have been updated, but I mean, it's important to understand we are here discussing about stuff that's been there for many years and it has proven to be robust, even though, of course, you'll see there are things that might need to be improved. And don't think that things are not improving. I mean, of course, in the 1980s, no one thought about mobile phones and 4G will be spread as they are now. Or maybe they thought, but at least they didn't know how to do it. Now we have them, but the beauty it is that we'll be able to implement 5G, not just 4G, 5G, and still your connections will travel inside TCP IP standards. And I think that's quite beautiful because it's one of these fields on technology that once you learn it a bit, you understand it. It's like there's no magic behind it. You might not know about a specific area. You might consider some areas a black box, like you might not know how the 5G in particular works, but you'll be able to grasp what happens when you actually type something in your phone and all these connections happens one after the other. So let's just start. What happens when you type google.com in your browser and press enter? Today, the first layer, of course, will be layer 1. It's the hardware one. Okay. And so the hardware one is actually the one that deals with the actual connection. And it's the one I will spend less time today with it. Okay. It's the one I will spend less time because actually you already talk a lot about hardware in Fab Academy. And the hardware implementations might depend a lot. What the hardware layers are? Well, we could have, for example, Ethernet, right? Ethernet, it's what makes networks popular. Ethernet is this cable, right, that new computers, they don't have anymore. It uses these connectors called RJ45, similar to phones. And you could connect it to your computer and to the back of your router, and suddenly you are connected. And in fact, even though it might look old school nowadays, when you think that your new laptops, they don't have Ethernet anymore, think actually that all the networks in companies, even inside data centers, they are built using Ethernet. In fact, inside buildings, we mostly use Wi-Fi, which is just kind of a version of Ethernet, because it does implement a lot of it, but it turns Ethernet, instead of being based on wires, into something that could travel through the air. We could also think, for example, on the way that your routers at home that you are now using to see me connect to the internet. Most of the routers nowadays, at least in Barcelona, I mean in cities, they use fiber optics, and they connect using something called fiber to the home or fiber to the cabinet. The most standard protocol is one called Gigabit Optical Passive Networks, GPON, GPON. So Gigabit Passive Optical Networks, which is basically a way of implementing Ethernet, we could say, over fiber optics. It does a lot of cool things. If once you want, we can talk about it, because the way that the fiber arrives to your apartment, it's really cool. Because there's not a wire from each of your apartments to the ISP, let's say, to the phone company. It's built in a way where it spreads, and it's quite an interesting field. But we'll leave it for another day. And just to finalize this list, I mean, if anyone wants to contribute any standard, 4G, right, it would be a layer 1 thing. Before 4G, 3G, 5G will be a layer 1 standard. Okay, in fact, a layer 1 and layer 2. I simplified the layers, as I said before. This will be a layer 1 and layer 2, and we could think even more about other standards that you might think, and especially keep in mind, as we said, and we'll start to see today, when we actually travel from our house to Google, you'll see actually how all these layers, they actually keep adding ones on top of the others. So what we'll see at the end is that, as you can see here in orange, that's the data I said before. That's the search we're doing into Google. We have a TCP header that in a way tell us once we reach Google, what service we want to request and in what way. Then we have the IP, which would be actually the phone number we call into Google. More about it later. And then at the beginning, we have this in our house, we might have the Ethernet header, which actually defines, okay, how information travels from my computer to the router. In fact, if I am connecting through Wi-Fi, I will have an Ethernet header with in a way with a Wi-Fi header on top. It's not called Wi-Fi header, it's called the standard, which is 108.11, if I remember well, but that's how it will be built. So let's say that's what enables us to actually build the internet. And that's really important, because keep in mind, we have the internet, it's not a network, it's a network of networks. There's not a company, there's not a government that runs the internet, right? We don't have United Nations running the internet. We don't have Google running the internet. We just have a bunch of people who agreed to connect their networks together. And so to connect their networks together, they need a way that let's say one country might have their systems working fully in fiber optics, another country might have their systems working in fiber optics and another technology, and you need things to communicate one with the other, no? I mean, I don't want to repeat too much, but I think it's obvious, right? When we do, as I said, for a search from the street, imagine how many times we switch from the radio links of 4G to actually the fiber optics network of your internet service provider, to the fiber optics network that might cross the ocean, to the Ethernet network of the Google data center, etc., etc. And all these back and forth without moving out from the idea of TCP/IP, just by staying on IP and replacing the layers below. So layer 1 is the one, in fact, that we could say that keep changing all the time in modern networks. You could even change other layers and encapsulate them, but we don't want to go that much into it. We'll go about it later. But layer 1 keep changing all the time. And that's actually what allows us to build the internet, right? With some of you already discussed this map. That's the Internet Exchange map. And that basically shows all the points in the wall where networks from different internet service providers and different companies join together. So these are not the only ones. There's even other places where this might be happening, but that's a nice representation of them. And in this point, you need to imagine is where, for example, if we talk about Barcelona, the networks of the internet service providers here, you could imagine Orange, Movistar, Vodafone, etc. They join together with other providers that could be providers at a low, for example, to do a long distance. So you might connect there with a provider that it doesn't sell to customers, it just sells to other ISPs. One, for example, that dedicates of sending your packages to Paris or your packages over the ocean to the US. But you can also talk directly there, and this is getting common with the company. So Google, let's say, might deploy in these internet exchange points their own fiber. So that means that at the end, when Vodafone, when you from your house through Vodafone, you want to do, let's say, a search into Google, it will be at the internet exchange point that's the nearest to your apartment where this connection happens, right? Between, let's say, your internet service provider's network and the Google network. And again, all these by changing mediums, by going from Ethernet to fiber and from fiber to whatever. And so that's one of the beauties of what we want to discuss today. So we're gonna start in a way to get a little bit more close to how these things work. Let's start to dig in a little bit what happens, right, when we actually connect to Google, no? And to do so, and to see a little bit how these connections happen, and so you see I'm not lying to you, we could actually go and do a test. So first of all, well, let's see what happens when I type google.com, right, in my computer. Please, everything I'm going to do, you could replicate it now if you feel comfortable. And if not, you could go and then afterwards, you could watch the video, quickly jump from one to the other and just also reproduce it again. So let me just do a quick, so I'll refresh google.com and you see like all the things you see here, it's basically this web page getting loaded. So it's actually this web page requesting a bunch of things from a server. And you'll say, why not just one? Well, because we are requesting the HTML for it, but we also request the PNGs for it, and we also request this other PNG that builds the icons, and for sure there's a bunch of other like JavaScripts, like all these things here, that at the end might be dedicated to track what we do, because as you know, Google loves data more than everything else. So you see this, no? So we are requesting something in Google, and in fact, we could see we request everything into Google, because if I go here and I actually go and put remote address, we'll see that we are requesting this to these numbers here, no? So 216-58-211-36. No, I could even make this bigger. You see, we are requesting this into that machine. So this is at the end, right, the phone numbers we are calling when we do that request. And this is a port. We'll talk about it later. We'll talk about what 443 means here. Let's check actually if this is true with another check. So there's a command that we'll talk about it later. So you don't need to in a way check it now, but let me just confirm, which I could tell us, okay, let me know the number for Google. And in here, I get the IP, which in a way is different than here. And that's because the DNS resolution might change from the one that Chrome is doing to this one here. More about it to research, in fact, after. In fact, you might see that at some point we are using. And this is important because it's important to understand, it just as a side note, we'll talk more about it later, that actually a service like Google doesn't have a single phone number. The same that in the time, let's say, when you used to use phones and not the internet, when you would call a big company, they will have a bunch of phone numbers and they will tell you, please call this one if you actually want to buy something, call this number if you actually want support, or even they will give you 5 lines and tell you if one is busy, call the other one. So the same happens to Google. They have a lot of different phone numbers and different IPs. So basically, it balances across all these. So now we know at least that to reach Google, we need actually to call this number here. Let me do something, or this one here. Both work. And in fact, I could show you this because if I actually go and type this here, Google opens. And if I go and type this other one here, Google opens. Okay, so let's say it's not that my computer is wrong here compared to Chrome, it's that they both get different IP addresses. And we'll talk about this, what happens after, because that's because of DNS, which is kind of the phone book of the internet. But let's do something quick. I will just use this one here. And let me just do what we call a host, a trace route. A trace route is a way of actually, well, first let me clear. Trace route. Sorry. So Traceroute, what it's actually doing, it's basically mapping all the jams that happens from my computer to Google. And that's, I think, it's one of the best ways to start understanding how networks work, right? I'm jumping from one machine to the other because between my computer and Google, there's a lot of small computers that are called routers. Like the one you have in your apartment, there's other routers around the world. They look bigger because instead of routing just your connections, they might route the connections of all the people living in the city, let's say. They could route up to millions of connections, and those are big machines that cost a lot of money. But basically, if we actually look at the results of these trace routes, you can see actually, I asked to trace route this number, okay? And just to confirm again, I put this number here and Google opens, correct? So this is Google. This is my local IP, and we'll talk more about this after. And so we're going from my local IP, that's the IP of my computer, into moving forward into the IP of my house, which is this one here, and then reaching to different networks till we reach Google. We could do a bit of more search for it. For example, if you go to system preferences, right? If you're on Windows, you go to your control panel, or in Linux, you can do an ifconfig. You will see actually here, this is my IP. I don't know, it might be quite small. If I go to advanced, I might see it better, right? But I go here and see my IP is 192.168.0.14. And this is the IP so if I'm that IP, the first IP I would like to reach when it will be the one of the router, which is 192.168.0.1. So it's the one you see here, okay? That's the IP that my computer in my home network, they will always reach when they basically want to go outside to the internet. Of course, they just want to talk to my flatmate, which is on the other room. It might actually sorry, let me mute comments on that. It might actually talk directly to it. But when it wants to go out to the internet, it always needs to go through my router. So it always will start by calling my router, 192.168.0.1. And then from there on, we might be moving forward to the network of my ISP. So in fact, if I do this, let's see if I could actually, sorry.
And why did it take so long to appear when you, like, the page loads instantly, but when you typed in Traceroute, it kind of like slowly, line by line appeared?
I don't know the full answer, but it is because actually it's not a tool that, let's say, by default, you don't know this information. In fact, I do know the answer because look, it's quite easy to understand. When I'm requesting Google, once I send my packet to my router, my computer doesn't care anymore about that packet, right? Or packets. My router takes care of this packet, and then the next router at my phone company, which is Vodafone, might get this packet and it will send it to another packet, which might be on the router owned, let's say already made by Google. And from that step it reaches the server. And then the message will go back, and then my router will finally receive again a reply and send this reply to me. But let's say my computer by default, it's not the one doing the process of jumping from one server to one server, right? Who actually does these are the routers in the middle. So in a way, when I do a trace route, it's the opposite. My computer suddenly, in a way, takes ownership of checking all the path that my message does. So it's a long process to do. would be in a way, right, if you are sending a message, a packet, and it goes through like different courier services, you are not aware of it, unless actually you want that they call you at each time and tell you, oh, I have your packet here. Oh, I have your packet here. So when we do traceroute, in a way, we're implementing a system like that, right, to trace the route, in fact, that's built into the name. And that's why it takes more. Is that answering the question?
Yeah, it makes sense. It makes sense.
And actually you could see the times. Well, I don't want to spend too much time on this because we'll go back later, but something we could do, but yeah, it's true. It's, let me just copy this, and I will show you on a web, which I have, I'll show you on a web, which I have here. It's called Traceroute Mapper. So that's a page that if I paste the results of a traceroute, it should help me to build a map of it. I don't know how good it is, but basically, in a way, it maps my connection to Google by actually connecting, by actually mapping all the paths. So basically, it says that until path number 6, I am in Spain, and then starting from the number 9, I am till the number 9. I'm on the US, okay? It does this by locating each IP, because of course, I could get any of these numbers and I could put IP locator, and you might find services that they have a database, they try actually to let's see. So you see that IP address, which appears in point 222 here, so in step 6, okay. This one in the steps number 6 here, this IP actually it's in Madrid, which makes sense, right? I'm going from my house to the node in Barcelona to the node in Madrid, and then I might be going, and still I'm in Vodafone Spain, you see? Let's look for another IP address like this one here, for example. It said there that starting from point 7, so I'll get A directly, we are not anymore in Spain, we are in the US. Let's find it out. You can see that's in the US, you see? It's important for you to understand the IP protocol doesn't embed on it any kind of Internet of Things protocol. It doesn't embed on it, let's say, a way to know where the IPs are physically located. There's not lat and longitude coordinates associated with IP addresses by default. So these are just databases that some companies are compiling. And you might guess why they're compiling. Well, they compile them because it's a good way to actually know where you are. So if I put IP location, this is getting my public IP, the one of my router, and actually tells me I'm in Barcelona. And this, of course, is used by many companies to locate where you are, even though you are not allowing them to get your location. They won't get GPS level location, but they will get at least in what city you are. Okay, later on we'll actually talk more about this. Okay, but I think it's important for you to understand that each IP address might have, of course, a physical location because the internet is physical, the cloud doesn't exist. We have servers and routers getting kilowatts generated with nuclear power or coal power or solar power spread all over the world, running the routers, servers, or phones or computers. And of course, those have physical locations. So if someone, as this company does, is actually capable of locating where this infrastructure is, then through the IPs, we could trace in a way how the internet physically spreads around the world. No, and that's what we are in a way doing now. So let me close this, and so we could move forward. So we did traceroute, okay? And so in a way, what I wanted to see here is that over all these IPs that we went, the medium, the hardware layer was changing for sure. So I'm on a laptop connected through my router on Wi-Fi, and my router, in fact, uses something called fiber to the cabinet, which is when your router uses fiber but through a coaxial cable, and then it might switch to a standard, let's say, fiber optics, and from that on and on, I will be changing not just the medium, but the standard. The standard, I mean that you might have 2 pieces of fiber optics that transmit light, but the protocols on it might vary. You might have, let's say, there's different ways, let's say, of sending data over fiber, and all these things will be layer 1. And so I think it's time to switch to layer 3. And why I'm skipping layer 2? Well, because as I said before, and let me just do it now so it's clear, layer 1 and layer 2, we'll consider them the same layer for that. So in a way, the explanation we just had is on the physical and the data link. in particular, if anyone is interested on a specific protocol, like Guillem, could you please explain me what fiber channel is? Or could we detail more about how wireless or Wi-Fi in particular works? We could do that after, okay? So please keep note of your questions, because I'm going over all the different, let's say, levels or layers on the stack, but then we can recover and enhance more on a conversation, and specifically on layer 1, because we could talk for hours about different protocols and I don't want to spend your time. If you have a specific question starting from layer 3, please, you can ask them directly, because I think it's good that we discuss about them just when we are there. So layer 3, that's about the network. And so the networks are about plates and numbers. Why? Because you might remember, because you know this level already, and we even checked it a moment ago. The internet is built into something called IPs, and most of the networks nowadays are IP networks. You might ask me how the networks were going to be 15 years ago. I might tell you maybe that some will be IP and some won't, or at least that's what the industry will tell you, right? The industry, it took a lot the industry to realize that you could do everything on IP. But nowadays, I think it's clear. We are doing Zoom over IP. It's not that I have a specific cable arriving to my apartment that delivers, let's say, Zoom services, as they thought maybe in the past. In the past, they thought that you might have the cable of your phone arriving to your apartment, but on top of that cable, you might have TCP/IP for all the internet services, but you might have another protocol for TV, another protocol for the phone. At the end, what we all discover is that on top of TCP/IP, on top of the internet, we could run all these services, and that's why it's getting more common that you get your TV over the internet, right? You have a device connected to your TV, or actually, or even your TV that are connected to the internet, and this, in a way or another, basically streams content as you do with your browser when you actually watch Netflix on it. And the same happens with phones, right? We all found that Zoom, in a way, you could make calls the same way we make them with phones, and there's even something called voice over IP, which in fact is the way that most of you might be getting the phone, in the case that you still have a LAN, let's say a standard phone in your apartment. If you have one of these old phones and you have fiber optics, this phone, in fact, is not actually a phone like an old school phone connecting to an analog line. It's just your router. It's behaving as an analog, let's say, it basically translates a voice over IP, so a telephone over the internet, into the old telephone protocol. So when you plug the phone into it, it actually behaves as a normal phone. And so in a way, you could plug all legacy phones into your router and still use them. But everything happens into your router. It's not that you have two cables inside your apartment nowadays anymore. So at the end, what we could say is that the idea of IP networks or TCP/IP networks, we'll talk about this on this chapter, actually spread globally, and it's used nowadays for most services. I had conversations with people, for example, on the engineering field, working with, for example, domotics and automation of houses and industries like photovoltaic systems, or, for example, on automation of let's say, of processes for the industry in general, a long time ago, or 10 years ago, about if TCP/IP was a protocol that suited them, and many of them were, oh, I don't know, that's good for the web, but it's not good for what we do. And in fact, if nowadays you check how Industry 4.0 it's let's say, driven, you'll see it's mostly everything on IP. So you'll see that the new robotic systems, they come with TCP/IP to connect ones with the others, and the new solar panels, let's say inverters and chargers, can talk TCP. And so let's say at the end, this idea that we need a specific kind of network for each specific kind of service, it's not anymore there. It exists for us, of course, for really specific fields, like why you want to put TCP/IP across two microcontrollers if it will take you that I can actually not even talk, let's say, IP, and that's why we have I2C, because it wouldn't make that much sense to connect a sensor with a microcontroller using TCP/IP, because suddenly the sensor will cost 10 times more than what it costs now. But this doesn't mean even that protocols are not trying to emulate more and more the ideas that were built into TCP/IP. For example, the idea that you plug many sensors onto a microcontroller and the microcontroller could discover them, etc., which were built on TCP/IP, are getting more and more close to this. No, so at the end we could say that unless really specific cases, the idea of implementing TCP/IP as a way to communicate machines one to the other, it's there and it's there to stay. So if you want to understand TCP/IP, we'll talk first about something that I don't know if you know that well, because in fact, unless you love computers a lot, sometimes you don't even realize. That's called the MAC address. And so the MAC address is a unique number that the hardware manufacturers of your Wi-Fi cards or of your Ethernet cards, so the Wi-Fi chip in your phone, the Wi-Fi chip in your laptop, actually got assigned by the manufacturer a unique number. And so these unique numbers are assigned because there's an entity that says Qualcomm, which is a big manufacturer of chips, or Samsung, or even, Apple. I don't know if they manufacture their own Wi-Fi chips. I don't think so. But other companies, you could imagine manufacturing their own chips. Or for example, you use the ESP32. So Expressive, the company, goes and says, look, I'm going to manufacture 5 million ESP32s. Please give me 5 million unique numbers. And so basically that way, by having a central authority that controls it, we ensure, right, that there's a unique number per each hardware device. And that number, in theory, the way it was built, it's written into your device. We'll check now with my computer, and you could do the same if you want. If you go to your phone or your computer, you could easily search for your MAC address. In your phone, usually it's inside some of the, let's say, in the general tab under, I don't remember now, but we could just check it on Chrome. You put MAC address iOS, for example, or Android. You will find easily the screen where to find it. So this is the screen where you'll find the Wi-Fi address. It's called in there, but it's actually the MAC address. In your computer, let me just, I'm on a Mac. You could do this on, so if I go to advanced, let me see if it's here. Yeah, Wi-Fi address, you see this number here? That's the Wi-Fi address. And in fact, usually even, as this is also part of the hardware, if you go to the About page on the system report and we go into networks, to Wi-Fi. Let's see if it's get it here. Yeah, so that's the config. That's my Broadcom chip. Broadcom is a company that manufactures the chip of the Raspberry Pi, but also the ones of the Wi-Fi chip on my Mac. You see MAC address 28CF, blah, blah. And actually, if I if I go back to the system preferences, I go to network, I go to advanced, and here it is. It's the same number, they finish with 91. Well, MAC address are numbers that our hardware needs because we need a unique identifier on the devices on a network, so we have a way to start playing the game. You could build systems that, sorry.
So this is not a dynamic address. It is
no,
fixed.
that's a fixed address, yeah. However, and your question is a good one, the point is that MAC addresses, as I said, were meant to be always the same on your Wi-Fi or Ethernet device, for example. The only thing here is that step by step, we found that MAC addresses could be used to track you really easily, because every time you join a Wi-Fi network, you are sharing with the network your MAC address. And so that's not a problem in the traditional idea of the LAN. Your computer stays at home, maybe after 2 years, move to the office and then back to home. 3 move in a period of 10 years. That's whole thing we used to move computers before. Now your phone, if you are traveling, might connect to, let's say, 10th of Wi-Fi networks every day. So it's leaving this bit of trace of the MAC address on each of these services. And that's important because people can start tracing you by knowing this. And not just this, you could in fact know the MAC address of a phone just not by joining the network, but by passing near a Wi-Fi network and having Wi-Fi open. This last bit, I cannot fully ensure if right now still fully is like this, but at the end it's important to understand that through the MAC address, we could be traced. And in fact, imagine how much information, let's say, hotels and airports have because you might change your phone every 5 to 1 year, but during that period, you might keep the same MAC address. So every time you come back to this airport, even before you actually tell your friend you are in the airport knows that it's you back in there. Of course, they cannot associate this number with you. There's not a database that tells that this MAC address in particular belongs to a MacBook that was bought by Guillem in 2012. But the importance is that at least they could recognize who's coming into a place recurring times. By crossing this, if I have information from the networks in multiple airports, multiple hotels, I could perfectly trace the travel that you did. That's why there's a new trend that companies start to randomize MAC addresses. I say start, but for example, Apple, I think on the last version of their OS does those, and for sure in Android you could enable it. And on your computer and any Linux machine, you could fake your MAC address. So you could invent any number, put it there. If you are really unlucky, you might match the same number of a device that's already on the network, and you might crash completely your network communications. You might need to change it. But it's possible to do. So imagine Apple has a range of MAC address, right? It all start the same. Let's say, in fact, we just saw it. Well, it's not Apple, Broadcom, for example, and Apple might anonymize within a specific range, I guess, all this. But the importance is that for a network to operate on a particular moment, let's say, at least for a standard network like the one we described today, we need these unique numbers to be there. You could get it from the manufacturer, you could generate it randomly, but you need to be there. And you need it because the first thing that we need to do is that once we are in the network, like let's talk, for example, about our home network, where I just have my laptop and I have the router sitting there. I need a way that my computer knows physically where my router is. And this happens because I need to use something called the ARP protocol, ARP, to actually know where my router is. So you remember before I said my router, and let's go for a moment back to the Traceroute, has this IP here, okay? So my computer needs to do an ARP request to actually figure out what's the MAC address of my router. And by knowing the MAC address of my router, then it could figure out where it is. That's I think, a quick way to understand why it is important. It is if you ever played a little bit with a network, the old school way, you might have a network switch, like the one on the back of your router, where you can plug multiple computers and printers and whatever you want in the back. Well, you could have computer A connected to the port B or the port 1, let's say, of your router or your switch, and then computer B connected to port number 2. But then suddenly you could decide that you move computer to a different port. And if both take the same IP address, they will figure out how to talk, even though if you are changing the ports. Well, this magic happens because your computer is sending ARP requests to actually figure out physically where each IP is. So in a way, ARP, if we actually think about a standard switch, right? If we think about a standard network switch, like this one here, which is like the one, for example, there's that IAC now, or the one you have in your home might have fewer Ethernet connectors, but works on the same way. When you change one computer from here to there, but they both keep the same IPs, and so they could talk easily even though you keep changing. This happens because there's the ARP protocol actually ensuring that the physical connection numbers are mapped. So this has a MAC address, this has another MAC address, this has another MAC address, this has another MAC address, and your computer has another MAC address. So it could perfectly link that the MAC address that before was, so IP, let's say 192.168.1.2, which is your computer, it's actually mapped on this MAC address right now, which finished with FE, and now it's mapped to this one, which finished with, let's say, 0F. And so it's the one that does this. Well, I don't want to talk too much about this because it's actually a really specific thing inside the way network works. But it's important for me to understand that below IP, that's what always we are talking, right? And we always talk about IP. Now we talk about this here, and we'll talk more and more about IP. Below IP, there's another level that's the our protocol that actually it's the one that deals with the MAC addresses to know where things physically are. And that's important because now we'll talk about IPs, and we'll see that with IPs it's a completely different game. So the IPs is who I am and who you are in a way, no? And so that's important because we need to know what phone numbers to call on the internet to know what page you want to open, no? And so basically, IPs are numbers that identify all the clients and servers, all the nodes, because at the end, the internet, that's important. The idea of the client and the server being two separate things, like my MacBook, it's a client, the Google is a server, it came after. But the internet was built in a fully decentralized manner. So your computer could be a server and your computer could be a client. And in fact, this day you tested on Friday this with Oscar, right? Because Oscar had a Raspberry Pi on his apartment that was acting as a server, but he could actually open Chrome and start browsing Google. So this computer at the same time was a client and a server, and nothing changed. It's not that you had to change the flavor of Linux or the flavor of Windows to do this. It's built into the core of it. So IP addresses. Well, the problem with IP addresses is that they thought that actually there won't be that many devices connected to the internet. So the combinations that the current IP address space allow us, it's a little bit more than 4,000 million devices. And as you could imagine, in the internet, there's more than 4,000 million devices right now. And so IPv4 addresses, I say IPv4 because that version of the IP standard, it's called version 4, and it's the one still used by all the internet, has a bit of limitations and help us in a way be aware of how sometimes we might invent technology that we don't know the impact it will have in the future, and then we might come out with limitations. No? And before I talk more about IPv4, it's important to know there's something new coming called IPv6 that actually solve that problem. But let's talk. Let's see for a little bit more about IPs. No, so IPs are these numbers here that we checked them before. Usually, the way they are organized and they were planned at the beginning. Of course, things change. It's that if this is an IP address, right, from Google. So the way that you do is that so. And we could see that. So look, this is the IP that let's look, host.google.com, and so this is the IP that we agreed before the Google has. It might keep changing because Google use dynamic DNS a lot. So that's the IP of Google, and so what the IP of my router, right? It's so the IP of my computer, and we could see it even if we go into system preferences, you could go to network, and you go to bands, TCP, it's this one here, no? So this is one here. And the IP of my router is this one here. If you are on a Linux computer, or you could do, or also on a Mac, you could do this, and you also get the same information. I'm doing some things through the graphical interface, so you don't see just something limited to knowing how to do it on the shell. You could do it also. So, so what's important to understand here is that, and now let me also show you what's my public IP address. So, so what happens here is that my computer does a request into Google, and because the IP is actually checking is this one here, right? That's the IP of google.com. For the moment, in my apartment, you might have a different one because Google has many IP addresses and servers spread over the wall. My router, which is here, knows that this IP it's not on the local network of my apartment. It's not the IP of my printer, for example. If actually I could even check if my printer is open. I think I have it on number 5. Yeah, you see, that's my printer, OfficeJet in my apartment. And so you might ask me, Guillem, how do you know that this IP is on your local network? Well, you see, they all start the same, no? And so that's what we call a network. So a network in the internet, at least as it was envisioned, always will have a number. and then you'll have a subnetwork, and then you'll have another subnetwork, and then you will also have the physical device. So each device at the end will have an IP number. No, so in my apartment, I could say I have 1 is a router, 5 is my printer, 14 is actually my computer. Okay, and so when this, which is my laptop, is actually requesting the IP here, which is Google, what actually happens is that my router knows it's not on its own IP range. It's not inside this network. You see, it's 172.217. So actually, it knows that all the IPs that are not within his range, it will actually throw them outside. It will throw them to the ISP. It will throw them to the ISP that, in fact, if I go to the Traceroute we did before, it's this number here. So what it does in a way is that my computer say, look, I don't know where Google is, okay, which has this phone number, but what I could tell you is that it's not in my network. And it throws this to the ISP first router that might be, let's say, in Barcelona. We could even check that IP address as before and check if it is in Barcelona. Well, it might tell us, look, it's not in Barcelona. Sorry, this router might tell them, well, that IP, it's not in my network. Look, it starts with 10. That's 172. So it will throw it away to a different to a different router. And step by step, but switching from router to router, I will arrive actually into here. The only difference of that router is that my router has a really simple routing technique, which is everything that's not on my local network, 192.168, I will throw it outside to the Vodafone, in this case, ISP router. The ISP router Vodafone could be more smart. It could know, for example, that if the IP starts with 172, it already needs to throw it to this IP. And in fact, this is what happens here in a way, because we send it to this number, which is the Vodafone router. The Vodafone router tells us, no, I don't have this in my local network. Check this other router, and then this router might already tell us, well, check on this router here, and from this on we'll be jumping and jumping and jumping. No, and you can see, and the only, let's say, thing that starts to differ here from the original internet is that it's a little bit weird in the way, because you might be changing here. We're in 172, and at some point you might be. Let me do it again. Let me do a trace route for this again here. And what could happen based on the original idea of the internet is that it's true that before, at the beginning, the internet IP addresses were allocated in a really neat manner. And while it does a trace route, I show you why I mean. Net block IPv4. So when the internet was built, let's say, maybe there's even a nice image about this, big institutions actually decided to share the network space in quite an unstructured manner. So all the IPs that starts with 12 were assigned to AT&T services, all the ones that start with 17 to Apple, all the ones that start, let's say, with 56 to the US Postal Service, and so on and so on. Nowadays, it's a little bit more blurry. And that's why, in a way, maybe I have some IP range in a location or by a data center operated by a company, and then some others. So it's not as nice maybe as before as you could map the things. I mean, still some exist. And if I do, let's see what happens if I do apple.com. I don't think I'll get any IP. Oh yeah, you see, it started with 17. You see the IP of Google, sorry, of Apple, host apple.com. It starts with 17. And if I go here, I see that 17 is it was assigned to Apple. So all the IPs within this range, right? Any number here from 0 to 255, from 0 to 255, and from 0 to 255, it's owned by Google. It's owned by Apple. Okay. You see, how do you get an IP address for your router? Well, your internet service provider owns or rents, in a way, a range of IP addresses. So I could see what's my public IP. I could show you ways of checking. I'm using a utility, but we could see if you actually go and type what's my public IP, you'll find You'll find a lot of websites that will tell you so. So that's my public IP, okay? And if actually I go and type this in here, you won't get nothing usually. But if you actually search for it in DuckDuckGo or Google, no, that's not because it starts. It's just, let me do it on Google. It's a bit better to search. You see, it says that this IP address is owned by Ono in Spain. So Ono owns, which is like a sub company of Vodafone, owns all this chunk of IP addresses. So all of you who are on a Vodafone network in Barcelona, if actually you go and visit What's My IP, you might get easily an IP that starts with number 2, and even that follows with 152. But this number, of course, no one else will have it because that's the one of my router. No? But we start to understand a little bit, I think, that we have these numbers across the wall. And for example, when we are at the Fab Lab, no? And then we talk with Neil and say, oh, Neil, we need to create a new server for GitLab because the one is getting old, you know, when we go to DigitalOcean, which is an internet service provider where we put our servers. We also use Amazon for it, but let's say we go to DigitalOcean and we start a new server in DigitalOcean. So DigitalOcean in a data center that starts a new machine for us. And in this machine, as DigitalOcean owns also a range of IPs, it will assign a unique IP for us, no? And so IPs could be assigned dynamically, but they need to be unique, and that's important. At a single time of the internet, the idea is that you don't have an IP more than once. You could do tricks with it, and companies do quite complex things to do load balancing and stuff like this that I don't want to add too much.
Can I interrupt quickly?
Yeah.
It's just a question. The VPN, like Hola.org and all these web pages that you like plug in, that are used as plugins to change your IP address, do they change, like, do they assign a new one, or do they change with, like,
It's a good question. I have a section dedicated to VPNs at the end, but maybe it's a good time to test it now. So what the VPN does is that it gets all your traffic and it tunnels this traffic to another IP address, usually the one of a server that's located on the specific country where you want your IP address to be. And then the IP you get publicly on the internet is not anymore the IP of your router, the one in my apartment, the Vodafone one I'm talking all the time sitting there. In fact, I have to say I'm using Vodafone as a name, but it's also from a cooperative called Some Connexion. I could talk about this more after. But so this router there has this IP, no, that I just showed to you, which is this 2, that we just, let me just open again. This, no, this is the IP of my router, no, that's on my Vodafone. If I actually run through a VPN, and for example, it's a VPN on the US, all my connection will go from my house to the VPN on the US. And then from the VPN on the US, I'll be browsing the internet as if I am in the US. So I won't get that IP address. I will get an IP address from the US. And I could show you this easily. So let me, what my public IP is. No, this is the IP, it's in Barcelona. No, can refresh, okay. Now I'll enable a VPN, okay. You could do the same test. You could install any VPN like TunnelVR. It's an extension for Chrome or any VPN to play with. I'll use another VPN I have here, which I could enable by doing this. Tunnel on. And now let me refresh the page. Oh, it changed. I'm in New York. How this happens? Okay, so you see, this happens because currently all my connections from my apartment through the Vodafone router, through all this network, are going tunnel to New York, and from New York is where I'm actually browsing the internet. So the internet thinks I'm in New York. Is that safer to browse the internet? It's not that much safer, because at the end, I mean, first of all, the VPN company in New York, if it's a company, of course, if you run your own server, VPN is different. It actually knows all the traffic that you and your peers are in a way connecting there, no? And in a way, the safety on the internet is already built in by this lock you have here on top, which is, or on the web more than the internet, which is using TLS. But it's a cool feature. I mean, VPNs, no, they allow you to jump from one country to the other, and in a way, they show how flexible the internet is. And it's really important you keep remembering the idea of VPNs, because in a few minutes, I'll show you more about VPNs, because it's important to understand how this idea of onions work, the VPNs. Let me stop this, tunnel off. And now refresh again. You see I'm in Barcelona. So, so just for the ones of you, what I did is now it's a VPN. It's not Tunnel Beer, it's my own VPN system, but it works the same way, in a way. I say Tunnel Beer or Nordic VPN or Express VPN. It's not a commercial service, it's my own, but it works the same. So let's go back to here, okay? We're talking about IPs. And so what's important to understand is that at the moment in the world, we are in a moment of a scarcity of IPs because 4,000 million IPs is not enough for all the devices connected to the internet. If you check the statistics of devices connected to the internet, we'll see that there are billions of them, okay? So how we do that most of the time is by doing something called NAT, or basically by putting devices behind a router in a way. So as you saw before, my printer, my phone, my laptop, all of them are connected in my apartment through Wi-Fi to the same router, and this router has a single IP address that share across all these devices. No, the idea of that is that the internet was not meant to be like this. The idea was that the internet, each device, even if inside my house, will have a unique number, and so all the addresses could be public. And so to solve this, there's a new standard being, let's say, rolled for quite a few years called IPv6. And we could see actually, if I go and we put again, let me clear that, and I put host.google.com, you'll see I'm also getting not just the IPv4, but the IPv6 number for Google. And the idea is that step by step, without you noticing, you might be browsing the web using more and more the IPv6, and at some point we could kill that and start referring to things like that. And that will allow, for example, that inside a local network like I am now, all the devices have a public IP address, which will solve something which is really annoying when you are playing projects. And this is the following. If I do serve here, well, let me do it on my desktop, maybe it's a little bit funnier. So if I actually open, see if,
127, Guillem, you typed 172.
Oh, sorry. Oh yeah, 127, sorry. Yeah. So this, what you are seeing now here, that's my, it's my desktop served as a web page, no? And you could see that video playback here, it's the video I just downloaded before to add on the PowerPoint. And so you could see this is true because actually if I am going to my desktop, you see that this is what I have here. Let's see. So it's in a capture of yesterday with Oscar, we got a glitch. Okay, and you see this is here, and actually this is this image here, right? Well, this is in my local computer, and I could even put the IP of my local address, which we agreed before, it's .14, I think. Sorry, I'm stopping this, I shouldn't. Let me get again. Config Ethernet 0.1, sorry. Let me make this big too. And you see, yeah, .14, right? So if I put this in here, boop, 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 it works. And so if you will be in my apartment right now and you will open this in your browser, all of you in my apartment will be able to see my desktop. And so see how quick I could start a server and I start serving my web pages from my laptop. Of course, when I stop my laptop, the thing will disappear. But wouldn't it be cool on the internet that you could just share with someone an IP and say, oh, I have a website running on my laptop, check it for me, check it for you. That's really cool, no? But you cannot do so. Why? Because if actually check, that's my public IP address. Let's refresh again. Yeah, this is, okay. If I do this here, this won't work. And that won't work because this is the IP of my router. It's not the IP of my laptop. So if I want this to work, I will need to tell my router, any request that you receive, please don't keep it within you. Send it to this specific device on the network that has local IP 192.168.14. So I don't want to extend too much on it, but so you see what limitations we currently have, where due to that, I need to implement something called NAT, and that means that it's not as easy as all the devices they have an IP address. Sorry, go ahead.
You're saying that if we do that, like inside, if we were all in your house, we could have access to your desktop. So TeamViewer?
Okay, so TeamViewer, basically what it does is that it's an application that, well, first of all, when I say to my desktop, I didn't mean that the way I set it up, I didn't mean that you'll get access to my desktop with a mouse as TeamViewer does. What I said is that you'll get access to this thing here, no, which is like the directory listing of my desktop, no, which it's run by this server here that serves a web page out of the content of my desktop. But you're right. The TeamViewer solved this, and it solved this because basically what it does is that it runs some software in your computer that connects to a server which is on the TeamViewer's facilities, and then you connect to the server from another computer, and this server acts as a bridge. So at the end, what this system will allow, the one I described, is to connect from one computer to another without needing, let's say, a bridge, without needing a server in the middle. In TeamViewer allows you to do so because it implements a server in the middle. No, that would be the short answer, let's say. So if actually, and so of course, and with a server in the middle, I mean that you need a company, let's say, to run this, no, or a company or a friend, or you running the server, but in a way, it adds more complexity and more vulnerabilities, and so it will add also more, let's say, issues because more people could see what you are doing in a way. No, it's not, let's say, it's not a one-to-one connection. There's a third person in there. Of course, we could protect this, but the idea of a third person, it's there when we put a server in the middle, right? So let's see for a moment, no, this idea of the networks also and IP addresses, no? Well, how do I know if actually an address is alive or not? So I could do ping, which is a command for actually checking if another IP address in my local network or outside is alive. So if I do this, I'm pinging my router, okay? And it says, yeah, okay, I'm able to ping my router. Now I'll ping my printer. I know it's on this IP, .5. I know because I assigned it myself manually, that IP, to make it easy to remember. I could even ping myself on 1014. But what happens if I actually go and ping this number here? Sorry, this, yeah. There's no one there, no? And the same happens with Google. I could go again, I always use the Google example, because that way it's, let's say, it's easy to remember, let's say, for all of us. I could ping that IP address, no? But what about if I want to ping another, I will embed a random one, let's say, I don't know. Yep, I could ping it. This server is alive, but it just because randomly got alive. Well, because most of the IP addresses around the world are alive. In fact, Oscar, could you tell me what's your public IP address?
Yeah. I am 83 45 116 254.
Okay, so I'm pinging Oscar. That means my router through my computer through my router, it's actually checking that Oscar router in his apartment is alive, because that's the IP of Oscar. And in fact, we could even, now that we know it's alive, we could do a traceroute, no? And that's cool because Oscar and I will live less than 1 block away, 1 minute away, and we could easily see like how far the connection goes, no, to actually reach that point. So still it's working on it. So if I put this IP, for example, let's actually go to story, and So if I actually go to any of these web pages, like the ones that I showed you before, and I paste this, that doesn't include a map. So let's put IP locator. So I'll put here, this is an IP. Yeah, so you see we go through, that's a private address because it went through some data center. And that's a private address too, but here it's a public one. So it's taking time to reach, to do a trace route from Oscar to my apartment. What's true here is that we go from my computer and then which I'm in a Vodafone network, as I said before, and in here we jump to Telefonica. Oscar, are you in Telefonica?
Yeah.
Movistar, yeah. So here, so Oscar runs Movistar, I run Vodafone, and from one apartment to the other, we go from Vodafone, and we might switch at some point to the CCGG, which is the Telefonica network. Well, I don't want to keep doing trace routes for all the class. It's not meant at that, but I hope these things give you a little bit of clarity of how these networks work. Well, let's keep moving forward. As I said, and I think it's clear right now, no? We talk about the LAN, the local networks, we talk about the WAN. Well, we haven't yet talked about the WAN, but the WAN, it's what we use for wide area networks, or I think it's better to maybe call this the internet. And so we have our local networks and we have the internet, which we could say the internet is a bunch of local networks connected together with unique internet addresses inside them. So I could refer from one to the other. Compared to LANs, which a LAN like the one in your apartment might have, your computer might have the same IP address as the Oscar computer right now, and that's not a problem because these are local networks and the public IPs they have through their routers are actually public. So it's a network of networks, and so you might say, look at them, but how are we assigning the IPs on your computer? Because look, no, like. So I go to here again, and I see I have 192.168.0.14. You could do the same. You'll get some local IP address. And when I go inside IAC, I turn on my Wi-Fi and I get an IP. And this IP, it's like, is it written in your OS? It's like assigned, let's say, choose randomly by your computer? No, it's actually negotiated with the router. The router in local area networks, you could assign IPs manually, no? I tell you, my IP on my printer, it's 05, so I always remember. The IP of the multicam laser cutter in the Fab Lab, I think it's .16 or .11, so we always remember this one, no? And so, but of course, when you have a lot of people connecting in and out from a Wi-Fi network, for example, like in IAC or in the Fab Lab, we want these IPs to be assigned dynamically, no? And so there's a protocol implemented on top of it. That's the one that assigns IPs. So let's look for the moment at the stack, no? At the stack that we have here, no? So what we have here is that in a way, we have a system that, we have a protocol called DHCP, which is here above, that's able to assign IP addresses, no? So in a way, we have a protocol that it's able to, in a way, fix the protocol itself, no? And so to show you that this is actually going on, and that let me do two demos for you. One is that I will go here and say renew DHP lease, okay. And you see it took a while, and the number here appeared the same. Well, it appeared the same and not a different number for one reason. It appeared here like because actually your computer, it appears sorry, like the same number because of the MAC address. We talked about MAC address before, as you remember, and we said that the MAC address are unique per device. So when you do DHCP, if the service finds that you have the same MAC address, it tries always to assign you the same IP number. If I will change my MAC address, it will assign me a different, let's say, MAC address, sorry, different IP. But I want to show you that when you do renew DHCP lease, something is going on. That it's not. I'm not lying to you. That actually my computer is not inventing this number out of nothing. And to do this, I could introduce you to a tool that it's really, really cool. It takes a little bit to know how to use it. It's called Wireshark. And so with Wireshark, we can see what's going on inside networks. In a way, we could do all the class we are doing just by looking at Wireshark. So I will select an interface, in this case, the Wi-Fi interface on my computer. Okay, and what you see here currently, it's all the activity going on in my computer. Okay, all the network activity that's going out of my Wi-Fi card continuously. The first thing you'll see here is that scaring, because you don't expect that you look. Let's say I am just I'm streaming you the class right now. No, I'm not opening any web page, just Zoom, and you see how many information is going back and forth of my laptop all the time. It's a little bit scary, no? Later on we could see, and in fact it's easy that if we check for this IP here that starts with 34, we'll see it's the Zoom IP, and this might be the streaming connection. In fact, let me just do it now. It's called this IP. It's called 34.250.167.95, and let's try to see actually this IP who is. You see, this is the IP of Amazon Web Services, and that's because I have a server range in Ireland. And that's because Zoom, the company that provides the conferencing system, might be running their servers inside Amazon Web Services, which is the Amazon, let's say, system for, let's say, service for hosting servers. So all these connections you see here on the UDP port might be me talking and receiving back and forth packets from you, no? Well, I didn't open Wireshark to talk about this, but it's these things you could spend like a lot of days talking about everything. Let me just go and show you something. I'll put here, I will filter by a protocol. And so I could go here, type DHCP, filter, see nothing here. Now I will open my network settings. I will renew. Okay, you see, this was my computer requesting my router give me an IP, and it got an IP. Okay, and so it uses a feature of networks which is called broadcast, which you could use when you don't know who to talk. A broadcast means that it's a way on a network to send a message to everyone. So my computer could send a message to all the devices in my local network, my printer, my phone, and my router, with a DHCP packet that says, look, hey, I need an IP, please. I need an IP. I don't have one. Please give me one. And then it says in broadcast because it doesn't know how the network is built. It doesn't know I have a router even. And then my router might reply, oh, here is a free IP address for you. And it gives him an IP address. Okay, that's the important thing. And in fact, just to show you, if we could get assigned any number, no? And if you go here and you put it in manually, I could, for example, assign myself an IP that it's free. How I know it's free, let me do this. I don't get any answers, no? Looks like this IP is free in my network. I put that 15, I put okay. And if I currently, you'll see I could perfectly browse the internet. This works well. I'm browsing the internet and I'm on a different IP. It's 015, okay? But anyway, I will go back here and I will renew. So I want a DHCP, I want an automatic address. We see the packets going there, boom, 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 okay, okay. Wireshark, I don't want you to get, let's say, upset with it, but you see at the end, once you get the few details, how quickly you could see what's going on your computer, how quickly I could see where the applications I'm running, applications like Zoom, but also an application that is even built in the core of my operative system as DHCP. It's actually, we could see what is happening without even knowing the source code of that application, just by actually using Wireshark to monitor what's going on, no? I'll just for you to, just as a brief on Wireshark, it is an open source tool. Later on, I'll put on the links all the tools, and it's used massively by the industry. In fact, many, let's say, many things have been discovered thanks to Wireshark, because you could use it to actually sniff networks and look at vulnerabilities, etc., etc. Well, in here, I want to talk to you about routing, but we already covered routing a lot. You already saw how we went from a local address to the public address of our routers. We reached servers on the internet. Just one side note on the importance of how these networks are built, and the importance that even though it's true that the model that our house follow, it's a little bit more the one in the middle, because we might have, let's say, ourselves being connected. Let's say my house doesn't have multiple connections to the internet usually. No, I have my router is connecting to the Vodafone, in this case, network, and it goes out to a Vodafone router that might be located in Barcelona. So it follows a little bit more the model of the decentralized. But then it's true that when it goes into the other routers, the one that are after my router, the one that build the internet, the ones that connect the Vodafone router with other networks around the world, actually it's more distributed, because I could reach, for example, the US not through a single transatlantic cable. I could reach the US through multiple transatlantic cables, even going backwards through Japan and then back to, let's say, in China, and then back to the US through the West Coast. No, and so we could say that the nature of this routing system, it's a distributed one, even though it's true that or home network usually that you have a single connection. The first step is decentralized, but it's not fully distributed. Important also to know, I'm talking about network topologies. If we talk about governance, will be something really different, because it's not fully at this. Let's say if we talk about, for example, if I'm telling you that my internet service provider is a decentralized network, you could agree, say yes or no, but you are quite limited, no, in who you choose when you connect. So I don't know if we could say that the governance of these systems is that distributed. It's a bit distributed, but there's, let's say, big parts of it owned by a few, and so it's hard to talk about a fully distributed governance method. These images here, I'll skip them, you could look them. They just talk about what we said right now. I use really all images, but because sometimes, in my opinion, they are easy to understand than some much smaller ones. You can see this idea of the LAN. No, we are here, this local network could be IAC, for example, with the LAN switch that could connect all the Wi-Fi access points that we have at IAC. You might even talk to a local server like the like the YAC cloud, where you host images images and files you want to print or you want to laser cut, and you might be going through a router to the let's say to the internet. You might jump across different routers into different hubs and through different paths. As I said before, there's not a single path to reach a server, and then you might end up on a data center where you have a router and you also have different servers with different switches. No? So that would be the path of a request to Google, like the one that happens when you type google.com, which again is the answer we are trying to solve today. And this thing we said, right? These R2, R1, R3, so ugly drawn, I know, but this kind of ugliness, it's part of the network style of things. These will be the routers. Oscar router, we tested a moment ago, my router, your routers, and these local networks, network A, B, C, are the local networks on these, let's say, on each of the apartments of each of us, let's say, on each of the houses. I don't want to leave config because we did it. And there's something interesting here. That's the one that facilitates that you have not a public IP on your computer. The public IP is on your router, but you might say, Guillem, so I request Google from my local network on my computer. My router sends that request to Google. Google sends back the request to my router because the public IP then that Google knows where to return the information. It's the one of my router. How my router knows that needs to deliver that to my browser in my computer and not to my flatmates or to my phone, because they're all inside the same network. That's called NAT, Network Address Translation. I won't go too much on it. If anyone is interested, we could talk about it after. Okay. So now we have computers connected to computers, right? I use ping for it. I was able to ping Oscar router, ping Google. So both, we have a network of computers, one talk to the others, okay? The next step we'll do here is to understand, okay, what TCP ports are. And we could think about TCP ports as, or TCP, as the tracks that connect things. So now we set the motorways, right? We set the different, let's say, roads and routes that connect all different computers. We found they could be dynamic, static. We could have local ones. So we could think a local one would be, right, like a private motorway, no, just for cars that has some sort of a boundary to access the public roads. That would be a router in our apartment. But now we want to put the tracks on it. And so on top of that networks, we have two kinds of tracks. We have TCP tracks and UDP tracks. When I scanned before with Wireshark, I don't know if you saw, but you can watch the video after, you'll see that all the Zoom packets were UDP. UDP is a specific track that moves really fast, but you don't know if what it sends is getting delivered or not. It's kind of a fast shipping system, no, for shipping packets, but you don't know actually if the packets arrive. But if you are shipping things which are really cheap, you could just say that if you don't get it, I will send it again. No? So let's imagine that we have a truck that basically brings sand from construction site A to construction site B. Well, if one truck gets lost in the way, it's not a problem because we have one truck full of sand coming every minute. So, you know, we don't care, it's lost. Another truck will come and sand is not that expensive, so we move forward. Well, that's what Zoom uses. Zoom uses UDP because it's a protocol that's really fast. And in fact, if you're losing some frames, if I'm freezing for 2, 3, 5, 10 frames, you won't care. And instead, if I am sending you an email and suddenly a part of the email it's frozen and I don't know, you might lost completely the conversation. And that's why on the internet, by default, we don't use UDP, even though it's very cool. We use TCP, which is a protocol that when it sends something, it actually expects that the receiver will send back a confirmation saying, hey, I received the information. Okay. And so with TCP comes the paradigm of ports. And what are ports? Well, they figured out that once I know how to call Google, no, let's say, let's go back to our beautiful always. And so once I know how to call Google, I do this, no, and I could ping Google, ping. I need to, this is a machine, it's a server in Google. Well, that machine could run many services inside. It could run a web page, it could run a mail server, it could run a DNS server, it could run an HTTPS server. So I need a way, once I know that, let's say, where to go, I need also where to park. That's a little bit like if you are delivering, let's say, groceries with a truck, and you arrive to a distribution center, and well, you know the address of it, but once you arrive, you might have different doors, depending if you are actually there to load washing machines, or you are there to actually, let's say, leaf oranges. And so these are ports. And ports are numbers that are assigned on all the let's say, connections that we do. And ports were assigned to different services. So someone choose that the port for HTTP is port 80 by default, and the port for HTTPS it's port 443. And so you'll see, and we can come back to this quick example we did at the beginning, where I go here and I go to network, I refresh, and you'll see it's not just that I'm getting the IP of Google, I'm getting 443. That means call the server, and once you are on the server, access the door 443, what we call the port. No, I think that this metaphor is quite obvious. And this is in a way, it's the application running inside the server that will return the information and deal with my request. It's listening to this port 443. And so you could see this quickly, because if I actually use another amazing tool called Nmap, and let me do an Nmap on this Google server. If I do an Nmap on this Google server, it might take a bit, so we can keep talking. Okay, you see, it tells me that that server has 2 ports open. 443, which is the HTTPS, it's the one I'm connecting right now here, and 80, HTTP, because actually, if I type HTTP without the S, google.com, what it did here is that it actually requested Google into the port 80, and then it got redirected, which is the standard HTTP port, and then it got redirected to HTTPS, which runs on port 443. It's like you are arriving with your truck and saying, oh, I'm coming here to request some information to Google, and you go to port 8 instead. No, you need to be in a safe connection. We'll redirect you to port 443, and then please go to port 443, and you go to port 443, and you start your conversation. No, but it needs port 80 to be there, so you find the port, and then the port tells you, please go to this other port. No, and so you will say, okay. So all the servers on the internet, they have these ports open? No, it could change. For example, you use something called FabCloud, right? Host fabcloud.org. It's where Fab Academy servers run, no? And so if I go here and I do Nmap FabCloud, put the IP, you could put also the host of it directly, wait a bit. It will scan and tell us what ports are open. And what ports should be open? Well, HTTP, HTTPS, I think, because we run services there that mean the web. But I guess there might be other ports open that do other things that we want to do. And so ports, you could get any port you want. The only thing that's important, and I could show you here in a moment, it is. Oh yeah, this finished, sorry. So you see the FabCloud has HTTP, HTTPS ports, right? But also has the SSH port, which is a port that you use either for the GitLab, but also to access remotely the server and manage it. So it has an application running on the port 22 that's actually listening for you to start a remote connection with it to do something. It runs an SMTP port because it's a port that the server used to send emails, because this is a server. We want this server to send emails like, oh, Oscar, the server is running out of memory, or a message like, welcome to GitLab, that you receive when you register into GitLab. And yeah, this is, and there's some other ports that we don't even know what's in there. We could even test it. So I could put fabcloud.org and see if something is here. No, it's not an HTTP protocol there. It might be, we could request it in a different way. Well, these are ports, okay? And so, and a way to know if a port is open, in a way, and so you see that, I could use an old school tool called Telnet. And if I type, this is the IP of Google that we used before, and I type this port 80, it opens, you see? It's really hard to close, I don't know how to do it. Let me open a new tab. And so if I do instead, if I do this, but for a random number, it's not opening, right? And so basically, this is the number, and the numbers, by the way, if someone is telling me, well, Guillem, but there's much more services than just this four. You could go open Wikipedia and you could put Wikipedia, and you could put ports, numbers, and you'll find a list of all the numbers. Port, sorry, I think it's better. Well, there's an example there. List of TCP and UDP port numbers. And here you have all the list. And you could, for example, say, okay, we'll talk now, for example, you could say HTTP. Okay, we set the moment. HTTP by DS by default, we said port 443. You could choose another one, yes. By default, when an application requests HTTPS, it requests for 443. If you want to use a different one, you might need to tell it explicitly. In fact, that's why before, when I show you my desktop, I had to put the port here manually, like 8081, because I didn't use port 80. I use a custom port, no? Well, I don't want to extend too much on that, but ports. Okay, and now we do, sorry, go ahead.
Sorry, can I ask, why is some number missing? Like, why not every port are in use?
This is a convenience. It's a little bit like, I guess at the beginning people were choosing port just because they were, I don't know, like funny for them, like easy to remember, like the guy who chose the @ on the email. And now, of course, it's getting a little bit more hard because a lot of ports are assigned. So people actually, I guess, you might try to follow a certain criteria, you know? For example, it's common if you search for 808, sorry. It's not really here. If you search for 808, so in the range of port 80, it's the one for the HTTP protocol originally, and still a lot of ports that are on the range of 8,000 are used for web servers on development, let's say, no? It's, for example, a convenience that's followed, no? Let's say they put it so usually when you are developing locally in a web server, you always know that depending on the framework you are using, but it might start with 80 something, no, the port. But yeah, the good thing is that there's enough, it's not like IPs we are on the limit, there's enough ports. to actually host, let's say, all the services that we want to host. In fact, I have to say, and I want to be fair, I don't remember how this is defined. I don't know if this is like a 16-bit integer, or I don't remember. So it's enough big anyway for like ports to come and still be able to. And at the end, the standard ports that you need, that let's say that need to be agreed are not a lot of them. No, are like HTTP, HTTPS, let's say SSH, Cabreros, DNS, and other like ports. Well, now is where the fun starts. So we'll jump from layer 3 to layer 7. Why? Because here, as I said before, now we'll talk now about the application. That includes application, presentation, and session. And this is like group 765. So we always say I take the highest value. No, so we'll move from layer 4 to the layer. Let me check. Sorry, I don't want you to confuse you. Yeah, perfect. Yeah. So we'll use straight to the application layer. Well, what's the purpose of layer 7? Layer 7, it's what, in a way, makes sense of everything we said before. Because layer 7 is where the applications are. And in fact, we already talk all the time about this. Layer 7 is where the HTTP live, HTTPS live, SSH, even particularities of it, like the Git protocol. The Git protocol can run on top of HTTPS or run on top of SSH. So all the things that make the internet cool, because in a way give an application to that network, email, they are on layer 7, okay? Because it's the application layer. First of all, before we start talking about HTTP, let's talk about one protocol we haven't yet talked, and that's DNS, the Internet Phone Book. DNS is really important because imagine having us to remember that to actually open the Google, we have to type this IP. No, well, for sure we all will remember it. No, like in the old days where we used to remember the phone number of our parents, our grandparents, or 2 best friends, etc., etc. No, so DNS basically solved that problem. It solved that problem because when you type wikipedia.org, your computer runs what's called a DNS client that basically connects to a DNS server that will tell him, look, what wikipedia.org is under this, no? And this is something, in fact, that we did all like since the beginning of this session, because I type a lot of these commands host, and now I'll also show you one called quiz. So let's do a quick test for it. So I'll open this, no? I clear, and I'll go and do host, and I put again, I always use this. I think I should switch to using DuckDuckGo or another project that's more interesting, but for the moment, let's keep it this. So host Google give us this IP. As I said before, the IP could vary, but the important thing is that I need to be sure that if I open that IP, I am suddenly in Google, no? And for the 20 or 100th time, I'll check, and we have Google here, so it's Google, okay? Well, the way this happens is because my computer connects to a server called a DNS server and requests for google.com what IP I need to access. I could do it manually using that command, but at the end, my browser, when we type google.com, it does this automatically. So when I go here into network, it's hidden from us because it's not part of the web stack, it's below it, let's say. It actually does this to solve google.com into the IP numbers that you see here on remote address, okay? This is happening automatically. And so where are those DNS servers? Well, these DNS servers are like any server, like the Google servers on the internet. Some of them are owned by private companies, some of them are owned by public companies. By default, if you go to system preferences, if you go to system preferences or any of the configuration panel of your operating system, with DHCP, which is what we played with it before, you get also assigned DNS. So this means that the router will automatically assign you a DNS, and this DNS will be, I could remove it in fact from here, and I could renew, and I will get assigned from my router a DNS, which is this one here, which is, let me type it here as, so we could actually, sorry, let's type it. So it's 221.66.222.1, and let's see who owns this. I bet it's owned by my internet service provider, which is Vodafone. Let me close this. Yeah, this you see is an IP from Vodafone. So the phone book of the internet by default on a network, on a home network, when you do DHCP, your router will assign you a phone book that's owned by your phone company. That means that every time that you actually request where google.com is, this will be solved by your ISP telling you, okay, that service is located in this particular server. That's important because internet service providers like to know what IPs they tell you for a particular service, because if you put google.com, they might redirect you to a server, to let's say a path that's free for them. But you could change this. No, I could go here and put any DNS server. And in fact, the answers might even change. And that's interesting because if I do now host Google, you see it's a different number than here. You see, I got a different number. And we'll see now, I will install different, I could go to OpenDNS and put a different set of, OpenDNS is a phone book, let's say, that it's run by a, let's say it's not run by your internet service provider, it's run by, let me see, because this, I think OpenDNS got bought by, this changed. Okay, I'll put some other DNS. I'll put the Google DNS, which is called, you might remember it because it's 8.8.8. So I'll put the Google DNS, okay, here, and we'll see if actually the address that give me changed. No, okay, apply, and now I'll do this, and you see I get a different number. No, you see? And so depending on the phone book I'm querying, I might get sometimes different numbers. This happens for big services like Google, that they might announce over the wall using different IPs. In a way that the DNS requests on the area of Spain, they actually go to the data centers in Europe, and the DNS in the area of the US go to data centers of the US. Usually, if you test this for a domain that you own, like fablab.org or your supercoolwebsite.com, you'll see it's always the same IP, whatever the DNS you use. And in fact, that's important to understand that when you buy a domain, when you go and say, buy a domain, and you go to namecheap.com, for example, no, and you go to, let's say, Namecheap, and actually we are in Namecheap, and I go here, say I want to buy the domain onionstack.com, and when I'm buying this domain, actually, so onionstack.net, it costs 11 euros a year. Okay, it's cool, it's cheap, no? Let's move ahead. So onionstack.com, what I'm doing is that I am just, in a way, booking the right to register on the internet phone books a record, a name like this onionstack.com that points to any IP I want. It's like, it's not actually doing anything technically, no? It's a policy, no? It's binding, it's allowing you to register this. It's allowing you to be the one who can edit that record on the DNS or on the phone book of the internet, no? To say in a way. And just one thing here, there's another command that's called whois, and you could actually play with it. Whois, it's goes a step farther on DNS, and actually it reveals the public information that when you register a domain or when you book a domain on the internet, you need to provide. No? So I could do whois yang.net, and I'll get the information of yang.net. And in this case, we go here, boom, 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 no? And you find all the information about that provider, no? You see register organization of that domain, it's YAG, Barcelona. I could go and put, for example, fabcloud.org, and we'll see who registered it. And I go here, domains proxy, boom, 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 fabcloud, boom, boom, boom. Well, it's private, it's registered on GoDaddy. There's not that much information because many people keep this private. So, but you see a little bit what's behind this service at the end. We need to think that these are application 7. These are services that run on the internet. And then we have the web, HTTP, okay, which is a standard protocol we use, no? And going back to solve the question, what happens when we type google.com, no? Let's test it, no? Let's test it. Well, first of all, let's try to replicate, no, the call to Google, no? So let me close this and open a new shell. Okay, so I'm opening, sorry, just did it so we have a clean and nice shell. So first of all, and I'll split this vertically so we could have easily multiple paths, multiple windows open. No, so the first one, I need to resolve the address. No, so I'll need to do host the google.com. Okay, that's the IP address. No, well then I need to know I want to request Google using HTTP, and how I know that? Well, if you are browsing the web, you're using a web browser. If you are accessing Google, you usually access Google through a web browser. Your web browser by default will request any page like google.com in HTTP or HTTPS, unless you're going to specify it at the beginning through HTTP. Okay. Well, now the next step is to actually know what port I need to use for HTTP. So for HTTP, it's port 80, you see here. So we'll do a test and we'll use a tool that allows us to actually, let's say, send information on a specific port. Okay, now I will send what the HTTP protocol does, which is simply sending some characters, like some ASCII characters that say get and the page. So I'll put get, enter. See if it works. I think I typed it. Okay, you see, I type this and I receive from Google, no, a result, which in the result of Google, it's called, it started with HTTP 1.1.1, which means it's using HTTP protocol version 1.1 because I requested here, no, like to make it clear. I'm requesting this, no, in here, and it's basically taking, but it's returning me a 301 code. HTTP has codes, as many protocols do. The code 301 means move permanently, and it's telling me that please, I need to, it has been moved, and I need to go and visit HTTPS because that's done. So when I access Google using port 80 on HTTP, which is not safe, so if you type something, everyone else around the internet could spy on you, not just Google, it basically tells you go and connect to the HTTPS. In fact, the first move that does, it's not the HTTPS, it's telling me, please visit Google with the W's. So let's do a quick check and see if we actually could do. We open again a connection. Well, let me clean it so you see it. We open again a connection, okay. And now, wait a second, we'll paste this, but we'll tell, oh, sorry, we'll paste this, but I will tell Google that we actually want with the W's, no? Let's see what happens. Oh, okay, oh, here it works. Here it works. I receive all the web page from Google. You see, this is all the code that load the home page. In fact, if you are really, let's see if you can fit it. No, that's all the page that Google loads. No, you see, that's the full web page with all the code. No, and in fact, if you go here and you copy, let me show it to you at the beginning. No, no, so that's the return, and you see the return now. So I was mistaken before because I thought the redirect was because of the HTTPS. No, the redirect was because Google want us to visit the site with W's. No, so the first time I request, it told me, oh, that I redirect you to not google.com, so www.google.com. When I did that, I actually received a 200, and okay, and that means here it is the page, and after a 200, boom, the headers with some information. We don't check it for now, and then the page with the HTML you see here. So actually, I copied this, no, before. I just selected this and copied. And let's actually go here. Let's make this small. Let's type, let's copy it. Let's see if I could copy this. I could even, to be nice, I will do a pipe, but I'm doing it the old school way. So we copy it. Let's see this works. Yeah, perfect. Okay. You see the doc type HTML, no? Now let's save it as in desktop as a web.html, no? Boom, colors already, nice. I don't even have a formatter for HTML. Here, no, I don't have wrap selection with that, no, but we could open that. Okay, so let's go here, and I have here web HTML, the file, and let's throw it on top of my browser. And we have Google, you see, that's a file that we just downloaded, okay? So you saw actually how we use IP with TCP on top, which is our track. We got a track from my apartment to the Google server and tell the track, visit Google and go into door 80. When you arrive to door 80, please deliver the payload that I put into here, which is this one here, right? In this case, we found, in fact, that it's better from the beginning not to get a redirect to request with W's. And the track got filled with all this text, you see. And then if my browser actually knows how to render that text, because it knows how to render HTML, it actually, boom, loaded the text, which, as you can see, it includes more JavaScript than HTML at all. But this is, okay, and that's how it actually works. I think it's not that complex, as you could see. And it's beautiful because HTTP, let's say, it's a protocol that we could read. So now we could go into here. And we could see that now, if I inspect this, by the way, I'm using Chrome. Firefox has the same tools, maybe even better. I just got stuck on using Chrome some time ago for the developer tools. Every time that we see one of these lines here, right, it's actually doing one of these requests. And in fact, you could see it's almost the same because it says request URL, it says this, which is almost the same that we did in here. Let me make this big again. So it's almost the same that we did here. Let me just make this a bit bigger. This information you see here on the reply, for example, of these 200 OK, you could actually see them if you go into the browser and you see 200 OK status code, and all these response headers actually are part of it. We might get them a little bit different because of different clients we are using, but this is. And then for each of these, let's say, requests, we did that, no? So in fact, we could use the same process and we'll get the PNG, etc., no? And so that's how your web is loaded. And the interesting thing is to see that actually a web could be loaded from a single file, just with HTML, but webs turn to be so complex that they are full of many different files that are loaded. And I recommend you to spend some time on these tools because you will actually see it here, and you will actually see that when you go here, you could actually filter by different types of things you load. No, so all the things, either they are HTML, JavaScript files, CSS file, image files, font files, video files, they're all loaded using the HTTP protocol or the HTTPS protocol, which is what your browser knows how to talk. Does your browser talk other protocols? Some browsers start talking protocols. There's HTTP2 coming, there's WebSockets, etc. But at the end, more or less, when you visit the website, even if you're streaming music or videos, everything happens on top of HTTP. And you could see that because if we go to YouTube, let's say, and let's say this run, YouTube is so slow right now. Maybe it's because of, so I'm loading a video, and this video it's being loaded by HTTP2. Okay, so if I go here and I filter by media now by, so you see. Let me show to you here. You see, sorry, you see that requests that keep coming here. These are the chunks of video being requested the same way we did through HTTPS, one after the other, you see? So basically every few seconds, the JavaScript running on my browser triggers a request to YouTube, gets a bit of the video and puts it on my screen. And it connects the files all together so you don't notice any gaps on it, okay? And that's all managed by your browser. You're doing simple HTTP requests, okay? Well, I talked for a long time, so we are about to end. I think the last bit that you can tell me, it's Guillem, why DS? DS adds, basically implements a level of security in between the client and the server, because it's important to note that the internet was not built by default with the idea of security in mind. These were researchers, these were professors at university, and no one thought actually that security was something to matter at this time. Also because at these times computers were so slow that implementing all sort of cryptographic algorithms will just make the whole thing to be super slow. We are not in these times, so we could now run HTTPS, and we could now on other searches, and that's why in fact nowadays it's not just Google. If you type any website, even let's say the FabLab VCN website or FabCloud website, you always will see this. Oh, FabCloud, because I think it's sorry, GitLab.FabCloud. Sorry, this one had HTTPS too, etc., etc. No, and so HTTPS, which you see with the log here, basically. What it does is that and I show you this because it's part of the Onion system. It basically tells you, we talked about the TCP/IP model and about the Osi model, and I told you we won't talk about all the layers, so I jumped them. So now we are on layer 7, which is the last layer. But actually, if you look at the Osi model, what we do is that we use a sub-layer inside the application layer, which is the presentation layer, to add below the HTTP protocol a level of cryptography provided by the TLS or SSL protocol. TLS is the substitute of SSL. It's the more advanced, let's say, that superseded because it was found SSL had some vulnerabilities. And so, in a way, the beauty of it, as you could see, is that we were able to get HTTP at another layer on the onion that provided security among the client and the server. So it provided an encrypted connection between the two without having to replace HTTP by something fully new. It's just a layer that we put in between these. And so if you actually go and think again on this now, and on these models here on the onion, it's just adding one ring more on the onion. No, it's basically layer 6 presentation where we added this system. And just so it sounds to you, what we added there? Well, we added something called symmetric cryptography, which basically means that when you are requesting something, let's say to Google, for example, you are sending a copy of your public key, which is a key, a token, a set of letters that could be fully disclosed, to Google. Google will use this to encrypt your data and send you back the data. But this key that you send to Google is just for encrypting data. To decrypt the data, you need the private key that you are the only one who owns. So in a way, that's why public and private keys always come in pair. One allows a third person to encrypt the information, but the only way to decrypt the information and code it with your key by a third person is by using your private key. So your private key stays safe inside your computer, and the public key is actually the one you send over the internet. And then when you want to talk to Google, you do the opposite. So Google talks to you that way, and you do the opposite. And also these keys get exchanged frequently and generated frequently. So even if you are spying and you can get the public key many times, it's hard for you to behave as you are the one owning the public key. And so that's the when you implement symmetric cryptography, which is a super interesting field. I really recommend you to read about this because it's really fun. And just to finalize, someone before asked about VPNs. And again, another example of the power of the onion, let's say, of the onion rings. It's this, what we do with actually a VPN, it's that you are basically getting the full stack, the full onion, let's say, and you're putting it inside another onion. So you'll get the data, which is the HTTP request to Google, for example, or to whatever service you want to. You basically also include the TCP or UDP, in this case, TCP request. So HTTP on Google, on TCP on port 80 or port 443, on the IP of Google that we found before, 2 something, 1 something. You get all these and you put all these inside, again, another packet. That's the one that travels to your VPN server. So let's say it's like you get whatever you want to send, you put it into a box, then this box gets delivered to your VPN server that could be on the US, for example. And then on the US, they open that box, they get the smallest box inside, which is the one that actually contains a request to Google. They do the request to Google, put it back to the bigger box and send it back to you. And that's what a VPN does. So at the end, as you could see, it's like if you are telling me that you are making things safer because you are actually sending, let's say, your packages to your friends by sending them all through a shipping service, no? That will put things inside in a smaller box, to a bigger box, and then deliver the smaller box in the country. But you could use them. It's a way actually of making your friend think maybe you are in a different country, but actually it's not adding that much safety into it unless you use it in a clever way. And of course, VPNs could add a lot of safety if you use them on clever ways. But as they are so popular, I think it was good to add this bit. So at the end, I think now, the same for Google, you could imagine what we do for email or for other applications. And with this, we are done and open for questions. Sorry, because it took a long time.
And about the VPN, because you picked the Onion as an example, what about the Tor browser?
Oh, that's a good. So the Tor browser implements something similar to the VPN drawing here, but in a recurrent fashion. So instead of the VPN paradigm works now, your packet put into a bigger packet, sent to the VPN server, then open, request happens, and then back to you. No, the Onion router, it's like at each step of the network, you put it inside another packet. So it's a packet of packets, no? So the packet will start waiting one, and then you put another box and another box and another box. And the one who puts the box is not a central server, it's a distributed server. So I do a request, and to do that request to, let's say, Google again, it happens that I am actually getting my request, and I send it to you, and you, which you are just appear on the network, appear on this big Tor network in your apartment. Your service running on your apartment will put my packet into a bigger box and send it to someone else. I will put it into another box and someone else to another box. Still will reach Google. That way, it's really hard for someone to trace back that it was me actually the one who put the original packet inside the box and the one who actually will receive back the information. Because on the way back, we'll follow the same process back to it. No, is that helping to understand a little bit the way Tor works?
Yeah, but so it's more difficult to trace you back.
It's much more difficult, exactly.
It's not impossible.
Well, it's not impossible if you say that what makes Tor vulnerable is that you don't know if you could trust, like on any peer-to-peer network, you don't know if you could trust all the peers. You need to implement on top of it a system of trust for the peers. So the same that the FBI could know that you are downloading things via torrent, because actually it could fake that the FBI could fake, or the Mossos police here in Barcelona could fake that actually they are a participant on the network, like I am, which is sharing their videos for free on BitTorrent. They could be the same, and then they will see that my computer is connecting to their server to download videos. The same, I'm connecting to your computer to download videos, or to my friends' computers. And so the same happens to Tor. Some people could create nodes in Tor, which are, let's say, fake, in the sense that they have an interest on spying what's going on through them. And then if they implement a lot of these nodes, it's easy for them to start understanding what traffic happens inside. So this is one of the vulnerabilities of Tor, but at the same time, if the network is big, so if there's a lot of participants, if all of us will run a Tor node in our computer by simply browsing the internet using the Tor client, the Tor web browser, it will be harder and harder. Because I'm not an expert at all on Tor, but the more nodes are on the network, for sure, the difficult it is to trace what activity it's happening in there. Just as I'm saying this, and just a way to add and finalize this, I think now you could solve yourself what happens when you send an email, or when you send an MQTT message using your Arduino to the Raspberry Pi that Oscar had in his house, as you did last week. No, at the end, if you go back to the original drawing here, you are all doing the through Ethernet, through Wi-Fi, through fiber optics, going through multiple networks, always staying on IP, mostly using TCP, and then using the protocol you wish on top, HTTP, MQTT, and on top of that protocol, then the payload you want. You can use HTTP to download video, HTTP to download an image, or HTTP to download the text. The same, you could use MQTT to post temperature of an email, or for temperature, or to actually send a full text, or you could use the email protocol to simply send a text, or to send a text with images attached. And all these protocols support a bunch of attachments and a bunch of media they could deal with. And then I think this is for me a little bit like let's say a summary of the way that the networks nowadays works. I don't know if you have any other questions. I know it took us a long time, but I hope it's been useful and you could use it in the future for your research, not just for the purpose of a technology itself, but also as a way to actually question the way we build networks and the politics behind them.
Go ahead, Anton.
Yeah, just about the peer-to-peer, because you didn't talk much about it. Like, what about the DAT protocol or other protocols, new protocol?
So that's interesting. Let me put this image quickly. Peer-to-peer networks, the interesting part of it is that peer-to-peer networks built upon the internet, they all share most of the layers, as always we are saying. They are an application layer protocols. And so depends on what you want to do. There's different protocols and different systems. If you are interested in searching peer-to-peer networks, I'll suggest you start by looking at BitTorrent. It's quite old, but still it's in there, and you could use it to do many things. You could also, for example, use the IPFS network, which is good for building distributed hosting information in a distributed manner, similar to BitTorrent, but specifically focused more on sharing public content, more like the way the web does. All these protocols at the end, what they take advantage is that once you have all these first 3 layers solved, or 4 layers, because it's the 1, 2, so interface network, it's 1, 2, the network and transport. Then on top of it, you could actually add to build any application you want. And the way the peer-to-peer networks work, it's not, let's say, something new, because the internet was built to support peer-to-peer networks. The one that took the wrong direction in this case, maybe it's us or companies or all together, but it's not that we had to reinvent the web to actually run peer-to-peer networks. It's the opposite. Let's say peer-to-peer networks work by default perfectly, because peer-to-peer networks because the internet was designed on a distributed manner. So the TCP, the UDP, and the IP protocol, let's say the TCP/IP protocol, as it's usually said, it's designed to be fully distributed. So you could perfectly build all sort of cool distributed systems on top, like the peer-to-peers to systems like the one you use maybe as teenagers, like Kazaa or Emule or whatever, or BitTorrent, or much more cooler things like the Ethereum network or the IPFS network.
Is it actually distributed, or is it kind of decentralized because you have to go through your internet? So
well, exactly, that's the thing. If we talk at the layer 1 and 2, let's say, if we talk a little bit about how the wires work, the wires are at least in our apartments are not distributed, because to be distributed, at least we'll need to be able to talk to 2 peers at the same time, and your apartment actually at least your apartment connects with 1 wire usually, the fiber. But I mean, and not just this, but the networks that to have a fully distributed network will need the governance of the networks maybe to be more open. Right now, let's say, yes, I could set up a router that connects through fiber and through 4G. You could do this. You could put a 4G dongle in your router and load balance, so the connections go between the 2. But still, like, you'll be under the, let's say, the control of a few big ISP companies, maybe, So yeah, it's true that building fully distributed internets, it doesn't mean only to build distributed applications as BitTorrent, etc., but it means also to build distributed networks. And for that, maybe an interesting thing I haven't touched, because I don't want to provide you with too many things. It's the Giphy.net project. It's the biggest open network around the world that started here. And actually, if you go, for example, to Valdaura, you will see that we have some antennas in the roof, and part of the internet, before all, now it's mixed because there's fiber in Valdaura already, runs through that network. And that's a network of people that operates Wi-Fi repeaters that connect ones to the others, and so they built in a way their own network, and that's fully distributed in this way. So in a way, if you combine distributed networks, so the layer 1, 2, and maybe we could say even up to layer 3, and then you actually implement distributed applications on the layer 7, like BitTorrent, like IPFS, etc. Then you kind of start to build a fully distributed internet. That's and then even on top of that, you might need to implement distributed modes of governance, because it's not just about putting antennas and running BitTorrent systems. It's also you need to implement so people could actually manage the network in a way that follows some criteria that you want. If it's inclusiveness, or if it's openness, or if it's privacy, or whatever. Yeah. So so this is. I hope this is helping you a little bit to actually see a little bit more on that. I'll put 2 links I already had on HackMD, which cover this. One is on how to build a low-cost distributed internet, and one is on IPFS, so you can see a little bit more about these future protocols. But again, I think the most important thing for you, if you are really interested in distributed protocols, etc., is that you think that you don't need to look for the next standard, that you could build distributed protocols your own. Because this day you had a Raspberry Pi in Oscar's apartment, and you had your Arduinos, and you were able to talk to Oscar's apartment Raspberry Pi. So actually, if instead of 1 Pi, you put 2 Pis on the 2 houses, and you actually allow your Arduinos to implement the MQTT code in a way that they maybe send the messages to one Pi and to the other at the same time, so you have more resilience on the connection. You start to think that way. You'll see how actually, I'm not saying you need to do it at all, but you could actually build yourself your own distributed systems. It's not that we need to wait for the magic of anyone to arrive, because the internet allows us to do these things.
Very quickly, Guillem, I know it's also probably like a buzzword, but it's, I think, a quite important thing. Could you give like 1 minute intro about the topic of net neutrality?
Oh, yeah. Okay, I'm not, I have to say I'm not an expert on many of these specific topics, but the way the internet was built is that, what image, maybe this is a good image, is that, so these are the transatlantic pipes, that connect all transoceanic pipes, sorry, that connect the wall, and of course, we'll need to map on top all the connections that go through land, and then all the small connections that go through cities, and they go through towns, they go through buildings. That's the internet. Well, historically, the internet service providers, those who take care of the big cables crossing oceans, those who take care of running from city to city, and those who take care of the last mile or the last kilometer or the last meter delivering internet to your house, will just care about the layers 1, 2, and 3. So your internet service provider, what it would do is to give you an IP address. It will put your router and give you an IP address and then through that IP address, you are free to send TCP tracks, UDP tracks, or any new protocol that you put on top of it. That's the responsibility of the clients connecting to your router, your phone, your laptop, your printer, your Arduino, your Raspberry Pi. Internet service providers were not messing around with whatever you transport on it. Step by step, internet service providers are starting to do so. They're starting to actually look at you and say, oh, well, Netflix, if you pay us more money, you'll be able to be prioritized on our network. So people that streams Netflix in their apartments will receive it faster if they are in Orange than if they are in Vodafone. Or even if they are in Orange, they will receive faster the connection to Netflix than the connection to Wikipedia. Even if Wikipedia is faster on serving than Netflix, Vodafone or Orange or whatever company will prioritize this. And it's what's mean that not being neutral, because you are looking at the packets. And that would mean that if you are a small company or a group of friends or a community starting a new project, you might have problems because you are not capable of paying the fees that allow you to reach people, to connect people more than reaching, I would like to use, into, let's say, full speed. And so there's a lot, let's say, of movements on that. As Oscar say, if you put the net neutrality, you can go here, you'll write, and there's the It's the internet. Sorry, I forgot what was it. The internet final. I always spell it wrongly. Sorry. I forgot the name. But anyway, I'll share it with you after. So you could read more about this, and there's a lot of let's say there's different movements around it, especially because it's not a big issue actually if this is affecting the way we watch Netflix, but this could have much more deep implications because it could be up to a point where this might allow the ISP companies that always were neutral to start looking more into the information you're sent back and forth, and in a way to start being more active agents in the way that the internet is managed, That right now, the only thing they were meant to do for years was give me an IP, give me connectivity, put me on the net, and forget about everything else, And so this is a little bit the situation. And so, yeah, this would be, I don't know if there's any more comments, things you want to add. I mean, as you see, it's a really big topic. We could be discussing for years about this because, let's say, the world is built on top of it, we could say nowadays.
Great. Well, do you have any other question, guys? Any other comment?
About the net neutrality, what's the status here in Spain? Like, because it's discussed everywhere in the world, but sometimes I have the feeling because I have sometimes like connectivity issue in my apartment, and I have like the feeling that the only pages that are easy to get to reach are owned by Google and big companies. And sometimes I have the feeling that that types of net neutrality is already in place here in Spain, but I'm not sure.
So I have to say, I don't know that well. I don't know that well. I will lie you if I give you a clear answer. I think it's better you do your own research. I'm sorry, but yeah, as I say, I'm not an expert. I follow it, but I don't know the current status about how this is. But it's easy that these things start to happen. I mean, just by when you get, I mean, and it's before this, but just when you get assigned a DNS server through the DHCP, in fact, already your internet service provider conditions you through what routes or what path you are following to access different services, So even though you could change that, I mean that there's more and more control from internet service providers into this, and especially on the mobile phone market, because let's say it may rise a lot the number of connections, and in our phones usually we have less control about what kind of connectivity we are dealing with. No one actually spends time setting the custom DNS on their phones, let's say, and these kind of things. So yeah, for sure there's a lot that would happen there. We just care about getting things fast from the big sites that we love to use as Google, YouTube, and it looks like we don't care anymore about internals, so this might lead into all sort of things happening.
Okay, guys. So I think we can conclude the session. Thank you, Guillem, for the fantastic talk. Everything was recorded. I just would ask if academy students to stay because I need to talk to you for a second, and if you can call or message the others that are not here to come. And we can close it. Yeah. So
by the way, I forgot just one thing. I just came out. This is the website I wanted to show you. If you are into, because I had a lapsus. If you are interested in net neutrality, just visit Electronic Frontier Foundation. That's the best people is in the US on that topic, and many other things we talk about: internet, privacy, Tor, etc. Just this. Sorry, Oscar. Go ahead.
No, nothing. That we conclude the session. I don't know who is recording. I don't know if Santi or Edu is here. But again, Academy students stay. And if not all of you, as I can see, are here, please tell the rest to join. Let's see, we talk here in 10 minutes. Okay, we'll leave this open.
Okay, I'm leaving. Thank you all for attending. And if you have any questions, you could always drop me an email. Okay, it was a pleasure. Have fun and hope to all see you soon physically. Bye-bye.
Thank you again. Thanks a lot.
Thank you.
Bye.
Okay. Edu.
Aprovecho este interín para comentar una cosa aparte. I put it in Telegram, but, para también vosotros los instructores, que sepáis que la Generalitat está dando mascarillas gratis si tenéis la TSI, la tarjetita de Salud. Se puede ir a una farmacia y te dan una mascarilla de estas de triple capa desechable, te la dan de gratis y luego a la semana siguiente tienes 2 subvencionadas a 76 céntimos cada una cosa así.
Vale, gracias. También en el metro de Barcelona están repartiendo las mascarillas también gratis cuando vas en transporte público.
Muy bien. So you are going to say something, or we'll wait a little bit more?
Yeah, sorry. I said until in like 5 minutes so that everyone comes. I'm waiting also for Edu because the problem is that, well, all this will be recorded. It's fine, just to stop the recording. But either way, I can say yes, guys. When you join, put the video or something, and then I'll know that you are here, because otherwise I see that Armand, Antoine, Bruno are here, and I don't want to repeat things twice. Okay. So what we were gonna have the final project session, but this Guillem session like went further, so we won't have it. But still stay here for at least 5 minutes, and we will talk about materials for a second. It's about getting things from the lab and this type of thing.
Hello.
Hello. I think Oscar wanted to tell you to stop recording the video.